Hello, good morning, good afternoon, everyone. Welcome to today's webinar. I am Marisa Fraser Morera with Pion, and I will be moderating this event. So today, our webinar is titled Pion Predictor, and predicting absolute fraction absorbed and transforming dissolution and flux data into API and formulation related information, and will be presented by Balint Shinko. Also joining us today is Sam Lee. He will be assisting with the live Q&A. Sam Lee is our development scientist. Balint Shinko received a master's in pharmacy at Semmelweis University in 2007 and a PhD in pharmaceutical sciences in 2012. As part of his PhD project, he developed a skin penetration model that has been licensed and commercialized by Pion Inc. And currently, he works for Pion as the leader of the development team. His research interest is focused on the formulation effect of intestinal and skin absorption. And in these topics, he has authored and co-authored over 25 research articles in peer-reviewed journals and 1 book chapter. He is also an industrial consultant for multiple PhD students at University College London and Semmelweis University and Budapest University of Technology and Economics. He also holds an honorary associate professor title at Semmelweis University. Now, if you need any technical assistance during this webinar, just please send your query to the host or me via the chat function, and I will do my best to assist you. You are also encouraged to contribute to the success of this webinar by asking questions at any time during the presentation. And for questions related to the presentation, we use the Q&A function. Our speaker will answer them at the end of the presentation, or Sam will assist as well. And as your moderator, I will be posting as many as time permits. Any questions that we don't get to during the live presentation will be answered by email after the event. Now, just for your information, we are recording this webinar and we'll make it available to everyone on our website within 24 hours or so. And for those that register for today, we'll also receive an email with a link to the recording. Now, I guess without further ado, I will hand things over to Balint. If I think at this point we'll end our video feed and we will start our presentation. Thank you. Over to you, Balint.
Yes, thank you very much. Marisa, can you please share your screen? So, because the actual webinar will be pre-recorded, and then we will have a live Q&A session right after it.
Okay, ready to go. Thank you.
Welcome, and thank you for listening to this presentation where I will introduce our new software platform, Predictor. I will show how we process the data of various types of dissolution and flux assays, and will introduce our unique mathematical model to predict in vivo absorption rate and fraction of those absorbed based on in vitro flux assays. First, I will give you an overview of the software and how it fits into our product portfolio. Then I will provide a few examples of dissolution profile analysis. Then, after a short introduction to in vitro flux assays, I will demonstrate the flux profile analysis through the example of our irreplaceable band formulation, and in the last part of the webinar, I will explain how these in vitro flux assays can be transformed to in vivo absorption rate prediction. Predictor is an addition to Pion's fiber optic product line, so I wanted to start with the cornerstone, that is the Rainbow. The Rainbow is a fiber optic UV spectrometer that can collect and process UV absorption in 8 independent channels. The light travels through the probes and measures the absorption in situ, so inside the chamber, and data processing is happening on the fly, so the concentration is provided instantly. The collecting software of Rainbow is AU Pro. AU Pro is collecting the UV absorption data and processes the data to get time versus concentration profiles. Up until now, AU Pro was the only Pion provided software to process the data further and calculate solubility, dissolution, and flux related parameters. With the introduction of Predictor, we are providing a new and more comprehensive platform to process the time-based concentration profiles and convert them to essential information for the fiber optic users. So, to give a one-line definition of Predictor, it is an enhanced data processing and management platform that allows you to analyze dissolution and flux data to get dissolution rates, solubility values, precipitation kinetics, and predicted in vivo absorption rate and fractional absorbed ratio. During this webinar, I will show some of the essential functions of the software and will demonstrate the capabilities through screen-recorded examples so you get a feel for the use as well. First, let me start with data management. As mentioned before, the UV absorption data is collected and processed in AU Pro, and then the time versus concentration profile can be exported to Predictor. Once the concentration profiles are properly processed, they can be exported from the dissolution tab using the Predictor export feature. In the pop-up dialog, the user can select the channel and the components they want to export. This operation will create individual files for each channel, making it possible to import them into Predictor one by one, and making it possible to combine any dataset we like and process them together. Now that the export is done, we can go to Predictor, can create a new flux dissolution collection, and can import the data by clicking Add Data. Here we can select the folder where we have exported data and can preview any data in the right bottom corner and can check the assay parameters to be sure that we are importing the right dataset. Once confirmed, we can click Add and then import the data into Predictor. Now let's look at the general data handling in Predictor. On the left side, we get the properties list, where the name of the collection and the name of the individual dataset can be set, together with all the assay parameters that was imported from AU Pro. For properties that has multiple unit options, the user can freely set the desired unit of the property without breaking any calculations. Also, AU Pro metadata is imported with the concentration profile, so the calculation in the AU Pro data file can always be confirmed and connected to the Predictor data. The middle portion is a graphical display of the data with the same flexibility in setting the units on both axes. Zoom in and zoom out is possible by holding the Shift key and click and drag, as demonstrated on the screen now. On the right-hand side, the imported data is shown in the table format. Any data point can be selected on this list and can be excluded or included as needed. As the currently imported data is a dissolution assay, I will show how to calculate IDR. First, in the properties list, I select the right assay type, as this will determine the calculation that is used. Then, I check if all the parameters were entered correctly. In this case, the disk surface area was missing, so I add 0.071. Now I add the range and set the range by repositioning the markers. The intrinsic dissolution rate is provided in the results section. This example was showing the processing with a single dataset. Now I will import 3 more to show how datasets can be combined. I go back to the import dialog and select 3 more datasets, add them to the collection, and click import. Now all 4 datasets are displayed and the statistics tab is automatically provided. The active dataset is highlighted on the graph and the properties can be set individually. Once all dataset is properly processed, we can look at the statistics tab where the results are averaged and standard deviation is provided for all parameters. After completing the data processing, results can be exported in various formats through the export dialog. Data export to Excel will provide the calculated parameters for further processing, and Word doc or PDF can be used for reporting purposes. Besides these dissolution assays, powder dissolution assay can be analyzed as well, and if the assay conditions are set up appropriately, like there is solid access throughout the assay, the change in the surface area is negligible, and surface solubility does not change during the experiment, then dissolution rate and intrinsic dissolution rate can be calculated and effective particle size can be estimated based on the Nerst-Brünner equation. Here is an example of how this can be done in Predictor. First, a new dissolution flux data collection is opened and a suitable dataset is imported. Under assay type, powder dissolution should be selected, and then all assay parameters should be checked. Adding a range will provide the calculation automatically, and then the markers can be set to fine-tune the calculation. In the Results tab, dissolution rate, intrinsic dissolution rate, and solubility are reported, and an estimation on the particle number, the total surface area, and the effective particle size is also provided. Multiple datasets can be combined, processed, and reported similarly to the previous example. In case of precipitation happening in your dissolution assay, it can also be analyzed, and precipitation rate and induction time can be calculated. I will show an example on precipitation rate and equilibrium solubility calculation. After loading a suitable dataset in the new dissolution flux view, we should select the precipitation rate option. After a quick check of the assay parameters, adding a range will provide the calculation, and setting the range will adjust it to the appropriate information. In the Results tab, precipitation rate and equilibrium solubility are reported. This demo concludes the section on dissolution-related calculations, where I wanted to give you a snapshot of how we can deal with various events that can happen in a dissolution assay. Now I will move to the flux-related capabilities of Predictor. In the drug absorption process, the active pharmaceutical ingredient first has to dissolve from its matrix, as only the API in solution is able to cross biological membranes. Upon transport through several lipophilic barriers of the gastrointestinal tract, the API reaches the bloodstream. This is called absorption. As the API is traveling in the gastrointestinal tract, various amounts is getting absorbed as a function of flux through the specific membrane, transit time, and available surface area as primary parameters. On the following slides, I will show some basics of our in vitro flux measurement technology and how that can be utilized for in vivo absorption prediction. As we focus on flux, let's see what we mean by that. Flux is a measure of transport and describes the amount of API that has passed through a membrane. By definition, it is the net number of moles of particles crossing unit area per unit time, as seen in the equation above. The mass change can be expressed as concentration curve over time multiplied by the volume. This concept is used to calculate flux from our in vitro assay results. Flux can also be expressed from Fick's first law that provides this fundamental equation that is also utilized in our permeability calculations. Pion offers a wide range of in vitro flux measurement tools optimized for small volume studies in preclinical development or biorelevant volume studies for whole dosage forms. The core concept is the same for all assays. The donor and the acceptor chamber are separated by a lipophilic pampa-type membrane that serves as the permeation barrier for the API. MiniFlux is a newly released flux tool that is the flux addition to the MiniDT small volume dissolution bath. It has a similar donor volume range as the BioFlux, but can go further down towards the in vivo intestinal volume levels, and also has a full integration with AU Pro for RPM and temperature monitoring throughout the assay. The case study I would like to use to demonstrate the capabilities of Predictor is Abilify tablet, that is the original formulation of aripiprazole with the in vivo human fraction absorbed at 87%. We have used the 50 mg dose tablets in our microflux assays and scaled the dose according to the small volume of microflux. As for the assay protocol, we have used our media change protocol for faster state conditions in the donor side and our standard GIT pump membrane and acceptor sync buffer. First, let me demonstrate how flux values can be calculated in Predictor. I open a new dissolution flux collection and then import the flux data. After that, all parameters in the properties list should be checked and missing one should be added. Once that is done, the range can be added for the flux calculation. The range can be adjusted to the linear region of the profile. And if we have a second linear range, then we can add a second range and have both fluxes calculated and reported under the results. Multiple profiles can be analyzed and reported in this case as well, similarly to the previously presented examples. Besides flux calculation for comparison of formulations, acceptor profiles of in vitro flux assays can be directly used to estimate in vivo absorption rate and fraction absorbed ratio as well. In the last part of the presentation, I would like to introduce the concept behind our absorption prediction engine, provide an example of running a calculation, and show some stages of the model evolution. Our starting point was that for a given intestinal transit time and surface area, the amount of material absorbed across membranes can be determined from the sum of in vivo fluxes. Using the experimentally determined values of flux, we have estimated the in vivo absorption rate and total mass absorbed by scaling flux to the available gastrointestinal surface area. Given the in vivo dose, we have converted this to a fraction of dose absorbed as well. The fraction absorbed model concept is based upon the GUT framework, so the Gastrointestinal Unified Theoretical Framework by Kiyohiko Shugano. In principle, inputted flux data is converted to in vivo relevant flux by determining the surface area available for absorption from the species model in use, human by default in our case. Acceptor profiles are converted into flux versus time profiles, and based on the observed permeability of the molecule in the source flux assay, flux is scaled relative to the degree to which an API can be expected to access intestinal surface of the selected species. Fraction absorbed percent profiles are then given by the cumulative flux versus time. Going into a bit more detail on surface accessibility, the Predictor fraction absorbed calculation first upscales the flux measured in vitro according to the surface expansion factor, which accounts for the increase in flux from the plisate and villi structures of the small intestine. However, the degree of access a compound has to the total surface area of the structure is dependent on its permeability, so the measured API permeability is used to determine the amount of surface access for the API. Compounds with high membrane permeability are absorbed before they are able to fully diffuse through the villi structure, while compounds with low membrane permeability will diffuse through the villi and are exposed to both the plisate and the villi surface area. Circling back to the overall process of converting in vitro flux profiles to in vivo fractionally absorbed results, first the acceptor profile has to be imported into Predictor, then the permeability should be calculated from the donor and acceptor data of the same experiment, then all the relevant assay information should be set in the properties list, and flags for the best fit line should be applied. Once this is all done, we will get the absorption rate, the total mass absorbed, and the fraction absorbed percent information in the results section. Now let's see how this works in case of the Abilify tablet formulation and the microflux assay data that we have obtained. We start with importing the acceptor profile, enter the name of the collection and dataset, and set the assay type. Then we enter all the missing assay parameters and absorption prediction parameters, including the permeability data that has been calculated based on fitting flux and dissolution curves in Predictor to the data of the same assay. Then we apply the time markers to set the beginning of the intestinal phase of the assay and the beginning of the linear and polynomial phase of the flux curve. Once this is all done, then we get the predicted parameters in the results section. For the prediction, we were mainly relying on the acceptor profile of the flux assay, and we have used the donor concentration as well, besides some basic physical properties and assay parameters, but there is no need to run additional in vitro assays to get the prediction. On the next few slides, I will show the model evolution and the accuracy of the prediction on marketed drug product examples. The first version of the fractionally absorbed calculation in Predictor took flux profiles from experiments and only adjusted for the difference in the surface area between in vitro and in vivo, applying broad plysate and video expansion factors depending on API permeability. The drug products that were involved are shown in the table together with the calculated and the actual in vivo fractionally absorbed percent. We set the criteria for accuracy to 15%, so any difference less than 15% is considered to be a good prediction. The graph shows the same data with the orange dotted line as the linear correlation curve and the blue line as the theoretical perfect match between calculated and actual data. In the first case, it was clear that overprediction was an issue for certain cases due to low in vitro API removal, as well as the difference in unstable layer thickness between flux apparatus and in vivo. The second version of the calculation used values of permeability acquired from the flux assay to calculate the level of API accessibility to the video surface area. For unstable layer limited cases, correction for the difference in unstable layer between flux apparatus and in vivo was added based on the apparatus type and storing speed. Overprediction is still a noticeable issue in this case, but the model has improved significantly. The third version of the model implemented calculation of the relative proportion of the dose remaining in the intestinal fluid at each time point, allowing the proportional reduction of the calculated absorption rate for situations where intestinal removal is high. With this change, the overprediction in excess of 100% fraction absorbed is no longer an issue, and the model has improved further. Use of the third version of the model exhibited a significant underestimation of fraction absorbed percent for celecoxib. The formulation being tested was known to contain a significant proportion of nanoparticles, thus particle drift of the API in vivo was determined to be the main cause of the underprediction. This effect has been described by various papers as a possible reduction of effective thickness of intestinal unstable layer due to the particles diffusing into the upper layers of the water bundle layer. The left side of the image represents the case when particle drifting is not occurring, while the right-hand side represents the case when particle drift does occur. If particle drift happen or not, and if it has a significant effect or not, is mainly determined by the particle size and the amount of excess particles in the system. Series of experiments at different celecoxib dose levels indicated that the influence of particle drift on the in vitro flux was observable and measurable. Adjustments were made to the model, allowing the calculation to account for the increase in flux observed from particle drift in vivo. Once the model has been adjusted for this effect, the predictions for cell-epoxy formulations became accurate. Overall, the model seems to predict the in vivo fractional absorb ratio quite well on this limited dataset, and it is also encouraging that the linear correlation of the actual data and the theoretical perfect correlation overlap well. Still, we are working on gathering further examples through our own experimental work and through beta testing partners to extend the validation of this model. In summary, I hope I was able to demonstrate the capabilities of the software package to manage and process dissolution and flux data that was collected with Pion fiber optic system and could provide a snapshot of the parameters that can be calculated from the measured data. Also, our unique modeling approach utilizes in vitro flux profiles directly in the absorption prediction, and the demonstrated data shows that running in vitro flux assays with real formulations in biorelevant conditions can provide appropriate input for the model without any further complex assays. And with that, I would like to thank you for your attention, and I'm happy to answer any questions you may have.
Thank you, Bulent. Start my video here. We do have some time to answer questions. And again, as a reminder to our audience, you can submit your questions with the Q&A box on your screen. And if we don't get to some of your questions today, we will be answering them via email. So with that, I will start with the first question. Is the fraction absorbed? No. If the fraction absorbed can be predicted only for humans, or can it be done for different animal models used during early development or preclinical stages to screen formulations? Also, what is the accuracy rate on the Predictor software?
Yes, thank you. So, starting with the species. So currently, it's only human that is actually incorporated in the modeling software, but the platform is open from that perspective. So basically, any other species can be entered. We just need to enter the right physiological parameters, like physical dimensions of the plicate and the villi, and parameters like intestinal transit time or and the after-water layer thickness in vivo, and based on that, the modeling system can be used. We are currently working on entering a rat model as well, but yes, it's the plan is not to have it only for humans, but also for some preclinical species as well. In terms of the accuracy, I think the last couple of slides addressed that. Even though our goal is to really get to this plus and minus 15% range, that's what we consider as a good estimation. And yeah, like a perfect correlation is not really expected or provided.
Okay, thank you. Will it only predict fraction absorbed?
No, we actually, so the fraction absorbed, it obviously requires those as well. But initially, so in the software, we calculate first the absorption rate constant, and based on that, we also provide a total mass absorbed. So those are also provided in the interface as well, and those are also available.
Okay, thank you. Is the surface solubility? If the surface solubility is changing, then how to estimate flux?
The surface solubility, you mean of
if the surface solubility is changing, then how do we estimate flux?
So yes, so all the changes that are happening to the API or to the formulation, that must be captured in the in vitro flux. assays. Basically, the donor site needs to be prepared, and that assay needs to be run as biorelevant as possible, and that process should take care of all the changes that are introduced by excipient or that's happening over time to your API or to your particles in the formulation.
Okay, thank you. What is the precipitation model in the predictor? Is it a first order precipitation model?
Sam, you want to answer that maybe?
Yeah, we do use a first order model for modeling the precipitation rate.
Okay. Are formulation factors considered in the prediction? For example, for the same drug with different formulation strategies, the fraction absorbed will be different?
Yes. So basically, we have included one formulation, typically the brand formulation for each of those APIs, but we have data for the generic products as well in many cases, and so those haven't been included in the table. But yeah, absolutely, the formulation impacts the flux profile, and therefore, because we do the fraction absorbed prediction based on the flux profile, it does have an impact on the fraction absorbed prediction as well.
Okay. Considering whole flux profiles are used, how does the prediction handle precipitation events in the assay?
Excuse me, can you repeat this, please?
Considering whole flux profiles are used, how does the prediction handle precipitation events in the assay?
Sam, you want to answer that?
Yeah, so if you do account for a precipitation event mid-assay, then the flux profile you obtain will respond to the concentration change in the donor. It's based on the amount of clearance that you get in vitro setups, though, it's reasonably likely that in vitro tests may exaggerate precipitation events. Well, it's something we're working on in later versions of Predictor as well, actually, evaluating precipitation risk. So in later versions of the software, we should be able to evaluate whether a precipitation event will or will not occur in vivo situation from imported in vitro data.
Okay, thank you. How is the 15 milligram dose translated into donor target concentration for the microflux? Is there a consistent approach to enable microflux and macroflux studies linked to the same in vivo study?
Yes, so for the microflux, we are scaling the dose down, considering 130 or 150 milliliter of intestinal volume, and that's how we decide how much dose we apply in the microflux. And obviously in the macro, rather more in the bioflux or mini flux, we typically try to use the whole dose of the formulation. And in terms of like having a consistent scaling for the different methods, the real key is the unstable layer thickness in vitro that we have measured for all of our systems, and that is incorporated into the calculations. That's an important factor to get the same or similar predictions with the various models using the same formulation, of course.
Okay, next question. Interesting discussion, thank you. Was the fraction absorbed % model generated using the same dissolution methods? If not, what approach did you use to ensure they were as biorelevant as possible? For example, do you control based on dose and volume used by a relevant media? How long do you test for?
So yeah, I already mentioned the dose, and for the microflux, there is need to scale down the dose. Of course, in terms of the media, for passive, we use a media change protocol, having a 30 minutes SGF phase, and then converting the media to PA 6.5 passive full. And for passive, even though we don't really have too many examples of that, but that can be a passive full assay, or fast GF to passive model, basically. So yeah, we are trying to use the appropriate biorelevant media. As I mentioned in the presentation, there is a flag that we apply during the calculation that basically sets the beginning of the intestinal time. So you can have a 30 minutes, or even a 60 minutes, or 120 minutes of a gastric phase in the flux assay, and then you can add this mark for when the intestinal section starts, and then we have the intestinal transit time in the model, and that's basically the portion of the flux curve that's utilized for the prediction.
Very well, thank you, Balint and Sam. We've covered all the questions at this time. Want to thank both of you for your contributions, and all of our participants for being a great audience, and our speakers' time that made this interactive webinar possible. So be sure to check our website for updates on new webinars, application notes, and so forth. And thanks again for joining us today, and we hope to see you next time. Thank you, guys. Have a great day.